So we have somewhat unusual talk today. It's not really strictly physics colloquium, but it's a colloquium which will span many different things, physics, math, and music, which I guess will be in the center of all of that. And our speaker today is Martin Wilkens, a good old friend of ours. We have met many, many years ago. In 1978, he was still a graduate student in Essen. And then after getting a degree in Essen with Fritz Haacke being his mentor, he came to Warsaw for a year. And that was a very fruitful visit. The visit was fruitful in terms of work, but he also married a Polish girl. So that was another result of this postdocing year.
If I may interrupt, Kazik, when I came to Warsaw, you said immediately, well, the only reason why you are here, Wilkens, is to find a woman. Okay? Said, no, you are completely wrong, but you were completely right.
Okay, anyway, this was really a very hard time here. And I remember that Martin used to tell us that there are two kinds of cheese in Polish stores. One is called white cheese, the other yellow cheese. So that was the time. And then we've met again in Constance when I was there, and Martin was there as a postdoc also. And finally, he got the professor position in Potsdam, where is he now? And I think it's a great pleasure for me to see and hear Martin again. I believe he was last time at CFT also giving a talk on quantum games about, what, 15 years ago? Probably. Okay, Martin, screen is yours and we are all waiting.
Dziękuję za przedstawienie I zaproszenie do Centrum Fizyki Teoretycznej Akademii Nauk, but I will certainly speak now in English because otherwise I get confused. Yeah, in fact, it was a pleasure when we met at this very sad occasion of the memorial session for Fritz Haacke a couple of months ago. And then Kazik asked me to give a talk on my latest research results. And I had to tell him, well, there is not much because for the last 2 years, I had to become, so to speak, a YouTuber, learning all this, making videos and Zoom teaching and all these things. So there was no time for original research. And in fact, even before that, the topic I was working on a little bit is the gravity of light. There are many more experts in the Centrum of Theoretical Physics there in Warsaw than I could present anything new. So, but then I proposed that I could talk about something which is completely off track. This is the topic here, the physical mathematics of music. And in fact, Kazik said, yeah, so what? Okay, so go ahead and do it. And I said, well, right, I will do it. And I hope you hear something now. Inspired by Kazik's "So what? I don't care. Talk about anything you want." I decided, well, I will talk about the physical mathematics of music because this is a topic which interested me since 10 years or something like this. It was inspired by a series of lectures I had to give my experimental physics colleague, Alfred Gerhardt, and I was in charge for the theory. Okay. But this was more or less focused on acoustics and all these things, which does not interest me too much. Okay, so I had to dive into the background of where does it come from. In former times, until I would say the 19th century, almost everybody who went through the university system was educated to write texts on music and mathematics and physics and whatever together. I found it very interesting and that inspired me. Let's stop this. Did you hear something?
Yes, of course, Miles Davis.
Thank you. Yes, it was Miles Davis. So what?
Even more that we wanted because the music was so loud that we didn't hear you.
Oh, okay. So it was not important what I was saying. Okay, so the music was more important. Hi, Ivo. Okay, so this is the piece, and why did I choose that one, except for that Kazik said at some point, so what, just come over. it's here. It's hidden here. This is a piece written in D minor, but with this little what is called Dorian down there. So what is that? And now, excuse me if I'm a little bit redundant, but I cannot be sure that everybody in the audience knows what is a note and what is a pitch and what is an interval or a chord or so. I will go very slowly through the basics here. So you have learned the note names, certainly, and you also may be a little bit familiar with what is called the piano. So we have the keys of the piano here. There are 7 white keys per octave and 5 black keys. Why? Okay, we will have to explain that. And then down there you see the so-called stave notation of these notes. If you play the scale, this is the scale in which most children's songs are written in. Okay, so this is the so-called ionic scale. You start at the C and go up and then go down or back and forth. But of course, you can also start your scale with the D. Okay, nothing prohibits you from doing so. And this is then called the Dorian mode. Listen to this. So you see, when you go up, there is already a half step between this E and this F, and this is characteristic for this Dorian mode. Now, why? What for? Well, that is the mode in which Miles Davis and Isaac Newton meet. And they meet here. You recall that Newton, he was the first one who undertook a first systematic investigation of the decomposition of sunlight, say, in its spectral components. And then he ordered these spectral components from red to blue, as it is done here. And he also made some semi-quantitative measurements of what we would now call the wavelength. And he found that somehow the wavelength of this red stuff is more or less 700 or so, or a little bit more. And the wavelength of the blue stuff is more or less 400 or something like this. And then he said, well, no, it must be 800 and 400, because that would be an octave. An octave is a relation of 2 tones, say, in which the upper tone has double the frequency of the lower tone. That is an octave. And if you talk in terms of wavelength, it's just the inverse, okay? So that he was convinced that this has to be the case because the Almighty loves nice proportions, and he puts everything in a kind of harmonic fashion, so it must be an octave. And in fact, that he did. And in his famous Optics, the treatise here, I think it appeared in 1704, in book 1, part 2, if you open the page, you see this, okay? That's what is called the color circle, or the circle of colors. And start at this D here. You go up D, E, F, G, A. Can you see my pointer, by the way?
Yeah. Yes.
Okay, very nice. A, B, C, D. Okay, so that is exactly the Dorian mode of the diatonic scale. Okay, and then you look at the colors here. Red. Please concentrate on red, yellow, green, blue, and violet, or yeah, deep blue or whatever. So he didn't have enough colors to fill the Dorian mode. He just invented, so to speak, in between red and yellow, the color, not he didn't invent it, but he put there orange at this half step. And between blue and violet, he put in indigo into the color circle. He didn't put it there, but he just named the corresponding tone of the color indigo. And now he was happy, because now he had his 7 things here, which he needed for the Dorian mode, and everything was fine. Actually, Isaac Newton in 1704, he published this, right? Right after the Principia. But even when he was a young student, he was working on musical problems. What you see here is it's written there. It's a page from Newton's notebook, undergraduate notebook, later titled Of Music. It's dated 1665, so many, many years before optics or the Principia. And what you see here are meticulous calculations of certain musical intervals. In fact, he was also doing experiments with the monochord. this is this device you all had in your experimental physics 101 classes, where you essentially show what happens if you divide a string into two parts and so and so. So he did all this, and he made some very meticulous calculations of some intervals. I did not really understand completely, I mean, only, let's say, 80% of what he's doing here, but I found it very remarkable. I found this page, say, in a very interesting book by Peter Pesich, The Music and the Making of Modern Science. I strongly recommend that to you as an audience. In fact, he, at the same time, he also read a big piece of book, namely the Harmonices Mundi by Johannes Kepler. This, I think, has been published 1619, and as you recall, this is the book in which the three laws of planetary motion are laid down: the ellipse law, the area law, and the period square is proportional to the cube of the greater half axis of the ellipse. But if you open this book, you will not find for any formula. Okay, there is no formula there, nothing. There's only text, very much text, very beautiful text to read. I really recommend. I have it here actually. Okay, and show you. Look, here we go. This fat. Okay, if you open this, for example, on this page, now you can't see that, so I have prepared a little bit here. If you open this, you see lots of this stave notation of notes and melodies, and now you hear something. If this is too loud, is this too loud for you? Do you hear? No?
Yeah, it's a bit too loud.
Can I speak? Can I continue? Okay. What he did is he translated, so to speak, the elliptical motion of the planets into melodies.
Yes, it's too loud, yes. So we cannot hear you.
I will wait. Actually, I will stop. I will just stop here. How can I stop this? Okay. What you would hear now is the melody. Are the melodies the planets sing? What he did is he, at the aphelion, when the planets are far away from the sun, they are, as you know, slow, and if they are in the aphelion, in the perihelion, they are fast. So this fast, slow, he translated into melodies, and then he put the melodies essentially on the staves. And the more eccentric your ellipse is, the higher or the larger is the step from the lowest here for Mars, for Mercurius, for example, to the highest. Venus, on the other hand, has an almost circular orbit, so it stays on the same note. I could play that now together, or it's a beautiful so-called harmony of the sphere, or music of the spheres, as it is called nowadays. Then there are still composers who essentially do that kind of music. The funny thing is that why was he doing that? He was doing that because he was can now see you. Okay, he was doing that because he was a little bit frustrated. His first attempts to put everything into Platonic solids, you know, this beautiful picture where you have these Platonic solids stapled into each other, that didn't work. And he tried to understand the purpose of this construction of the universe. The principles the Almighty has implemented to do this beautiful universe, he wanted to understand that. And then when he found it's not a circle, as has been proposed by Copernicus, Nicolaus, but it's a ellipse, he tried to find out, okay, ellipses are not as nice as circles are. So, and then he came to the idea that, in fact, the Almighty is not doing geometry, but he is singing. And now he wanted to find out somehow the rules of this singing, and that's the reason why he put this into these melodies. And he was very happy. And there is even this phrase somewhere in this Harmonices Mundi that he kind of understands now the purpose of the Almighty, because if you look at Terra, which is here the Earth, it sings the half-tone step. And if you recall your solfization, which you may have learned in your choirs, this is this do, re, mi, fa, sol, la, ti, do thing. Mi, fa is the half-tone step, and this stands, like the Earth makes, and this stands for miseria e famina, so misery and hunger. And in the German, as a German Protestant, he would say, "Die Erde ist ein Jammertal." And somehow now everything is falls together, and he says, well, that must be it. Okay, that's the idea the Almighty had when he was creating the world. Let me continue. This is another composition, but it's more recent. In contrast to Kepler's celestial scores, we have a musical score here, which is man-made. Anybody has any idea who did that? I can only tell you as a little hint, it's a very famous physicist. I wait for 3 seconds. No? Okay, okay, before I tell you just the melody, it's pretty boring. In fact, this was a composition made for a research project. And the person who did that is this one here. This is the young Max Planck after graduation, or just after the graduation from Munich. Then he, he became a scientific gypsy. He was here and there. He became associate professor in Kiel, and then he got an offer to University of Berlin. He accepted the offer. Essentially, he was following Hermann von Helmholtz because Hermann von Helmholtz retired at that time. So this was Max Planck. The composition dates 1893, and the research project was the following. You know, the good thing is that Max Planck was a brilliant pianist. So he had no problems in playing that here. Actually, this was not played on the piano, but when he came to Berlin, the dean took him by his hand and said, well, look, Max, this is your new office here. And there in the corner, we have a very big piece of equipment. It's still packed. I don't know, Hermann von Helmholtz ordered that, and we have to do something with it because the taxpayer paid for it. Please make a research project with the content of this big box. So Max Planck unboxed the big box and he found this. This is called an 8th harmonium. It looks like a piano something, but each key of your piano now has 5 or 4 or even 6 microtonal divisions. So this is a kind of precursor of a synthesizer, what he had there. And now the job was to do something with it. And what he did is the following. He invited 3 or 4 choirs, layman choirs from Berlin, and they were supposed to sing this 4-voiced composition you just saw. And his hypothesis was that if they sing according to the physics of their vocal cords, which implies what is called the so-called natural tuning, then if they start on a C, they end up on the same C, but with the pitch slightly higher. That would be the result of this of the natural tuning of the instrument, of the vocal cords. The choirs had to sing a cappella. So no instrument was accompanying them. The only thing what he did is that he tried to very carefully follow what are these people doing on his harmonium here, and could do that in a very careful fashion because he had these microtonal divisions. And then it turned out actually his hypothesis that the choir end up with a slightly different pitch than the initial one, that turned out to be wrong. They followed exactly, they came up exactly with the same pitch as they started with. That surprised him. And then he wrote, I think in total he wrote 2 original papers. This one with the title Natural Tuning in Modern Vocal Music, in which he put forward the hypothesis that these choirs, they do not sing in what is called the natural tuning, but they sing in what is called the so-called equal temperament. The equal temperament, I will have to explain that a little bit here. If you look at what is called the harmonic series of a swinging string, you all know that kind of pictures here. The lowest, the base or the root has this, let's say, wavelength, and it's swinging, okay? Call it C. Now, if you take the first harmonic to that, that is 1 octave higher. The frequency here on the right doubles. And then it goes on like this. This is 3 times the original frequency swinging here, 4 times, 5 times, 6 times. And you can order now all these tones in this kind of stave notation thing here. This means 1 times nu 0. This means 2 times nu 0. This means 3 times nu 0. And this 4, and this 5 times, and this 6 times, and so and so. And the so-called natural tuning is that tuning system in which all your, let's call it, all your keys on your keyboard are tuned only using 1 through 5. Meaning that the frequency ratios are always on the denominator and on the numerator of your frequency ratios of your intervals. You have products of these numbers only. And that's it, okay? And no 7 and no other prime numbers appearing. But it turns out, no, it's not the case. This kind of tuning, we don't sing, evidently. And his idea was, we don't do that. We sing in what is called the, let me switch here briefly. Oops. We sing in what is called the equally temperate intonation. Meaning that each halftone has a 12th root of 2 frequency relation. So in other words, this C sharp here up relates in frequency to the C here with the 12th root of 2. This kind of tuning the system, where all halftone steps are tuned in this manner, is called equally temperate, and it was in fact invented during the Renaissance, but it was not implemented until the end of the 19th century. And at the end of the 19th century, all pianos you had at home were essentially tempered in this manner, in this equally temperate intonation. And so the idea was that these choirs, they have been used by playing music on the piano or hearing whatever. They are used to that, so they are now singing in this mode. And then he published these 2 papers, and with this, well, the instrument was done. Okay, he could now turn to invent H bar and quantum mechanics on the 5th of October at 9 o'clock, 1900, somewhere here in Berlin. Okay. Now the question is, how is it possible that, as I told you, I have 2 examples, and in fact Max Planck is also an example, that all these people, if they write something about physics, they automatically write something about music. So how does it come? It's not so that Isaac Newton, for example, was playing an instrument, no. Or that he was in particular love with music, no. In fact, he detested music a little bit. I think he was once at an opera, he went out and said, no, this is horrible, I never go there again. So it's not the practical music what drives them, but it's essentially the curriculum of the higher education, which until the 18th century, 19th century or so, was still implemented at the universities. And this is called the so-called the 7 liberal arts, as they are called. I have written this in a kind of so-called Bologna fashion here. The goal is to develop intellectual and moral excellence. The goal was not to become a specialist in something. That comes later, after this master studies here. Later you decide either theology or how's it called, jurisprudence, law, or medicine. These were the 3 choices. And of course, theology was considered to be the best choice. But here, this is the master studies. You start with the grammar, rhetorics, and dialectics. First, you learn to speak in a proper way. Then you learn how to formulate convincing arguments. And then in dialectics, you learn how to argue properly with your opponent. Okay, then this is a year or so, or 1.5 years, or 2 years. And then you go into this, what is called the Quadrivium, and it consists of arithmetic, geometry, astronomy, and music. Now, if there is written music, what is not meant there is that you learn to play an instrument or something like this, but it is more, if you look here, music is that which links geometry to astronomy. In what sense? Well, geometry is the manifold of static forms. music is the unfolding of proportions in time. And astronomy is essentially both, okay? Forms moving in time. And arithmetics is just pure, let's say, elementary playing around with abstract numbers. So that made the Quadrivium, and all these guys I mentioned, they went through that school here, and they learned the language of music. The authors of this, were as I indicated here, Platon, Aristotle, Boethius, etc. Well, of course, there was no university in the Greek era, but somehow the ideas have been laid down by the early philosophers. And then finally it was formulated by Boethius in, I think, 6th century after Christ. And this whole thing has been inspired by the Pythagoreans, this brotherhood of, the secret brotherhood of these, let's say, not monks, but something like similar to that. In order to understand now a little bit more in particular, where does this come from, that we have 12 keys per octave, why 7 white and 5 black? Okay, that is Pythagoras. And what you see here is the School of Athens. This is a fresco by Raphael, where all the great minds have been depicted, and we will concentrate on, of course, Pythagoras, right? That's the reason why we are here. Now he is sitting here, and there is a scholar in front of him holding what is called a tablitza, or a blackboard, a small blackboard, and there is a figure written there, or drawn there. It's a kind of Feynman diagram, okay? We will have to decipher this now. And below this Feynman diagram, you have this very boring 1, 2, 3, 4 pedals or whatever symbol. This is a sacred symbol for the Pythagoreans, because they were convinced that everything you can reasonably talk about must be related to this lower figure here, which is called the tetractis, the fourfoldness. Okay, so here again we go, and they derive now from this tetractis the so-called standard model of, let's say, of music, which is still with us until today. It is very similar. If you go back here, this lower piece, yeah, is very similar to the decuplet of some baryons here on the left side. So we have not changed much. Okay, so this is let's call it the multiplet of everything. There is this famous quote by Philolaus that indeed all things that can be known have number. I have even written it down in this Greek manner here. The good thing is that if you are a physicist, you can read Greek. Okay, and mathematicians too. But if you study some other subject like economy or so, you have no idea. Right. So let's go back here. This is 1 pebble, 2, 3, 4, and from this you can make, let's say, relations of fractions. Yes, 1 to 2, and 2 to 3, and 3 to 4, or 4 to 3, and 3 to 1, and 2 to 1. Now the idea is that all musical tuning comes from that, okay, because this is the source of everything. This was the conviction of the Pythagoreans. And there is this legend or story, this anecdote, Pythagoras in the smithy. So he is taking a walk at some day, and he walks by a smithy, and there are these blacksmiths. They are hammering on metal, and he realized that sometimes it happens so that 2 blacksmiths hammer at the same time with different hammers, and then sometimes it sounds nice and sometimes it sounds ugly. And so he, according to the anecdote, he went home and made own experiments. You see all these here with the strings and with bells and with flutes. And we are going to do this experiment now, but we don't. We essentially take a monochord, and you see here, this is the chord. The string length is 1, okay, arbitrarily. Back here on the right side, this is the octave. The string length is 1/2, and only later, only this piece here will oscillate. And here we have 2/3, and here we have 3/4. These are the numbers allowed by this tetractis, by this fourfoldness. Okay, let's do it very briefly. So this one, this fine. Now let's do two together. Octave looks nice or sounds nice. Okay, let's connect it. This is the fifth, the musical fifth. Sounds nice, connected. Fourth, sounds nice. Oh, another fifth. Okay, fine. Another fourth. Okay, done. Now, if you take your string length not 1, but let's say 12, then of course you know that the octave is at 6, which is half. And now if you just look at what we just did, you realize that these relations we had for the musical fourth and the musical fifth implies these kind of string lengths here, and they are exactly now in the so-called arithmetic and the harmonic mean of these numbers. So that was very satisfying for the Pythagoreans, that they essentially could connect what the tetractys says to what they know from other subjects, the various geometric means. Now there is a so-called geometric mean, which the prescription for which you can find down here. It comes essentially again from Pythagoras. He introduced this notion. Anyway, the harmonic mean, by the way, we are well familiar with from calculating the effective mass in a two-body problem, or the effective resistance in a parallel circuit. We know this. Okay, now let's look at this tritone, as it is called. It is up here, and if we now hit here, it sounds ugly. So it has been thrown away by the Pythagoreans. And there is even the legend that until the late medieval ages, you were not allowed to play music or make music or sing using the tritone, because it's the devil's tone or something like this. Right. Now there is one thing missing, and this is the so-called Pythagorean full tone, or tone just. If you can now make melodies and all this kind of stuff. Melody is just a sequence of interval steps. And in interval steps, we know there is the fifth going up, okay, with this 5, and the fourth up, okay, this is this one here. And if you express this as a kind of a frequency ratio, you find the fifth up is 3/2, and the fourth up is 4/3. These are these numbers allowed by the tetractys. And now a melody is just a sequence of interval steps. Let's make this sequence here. We go from this F to the C down to the G. From F to C, it's a fifth up, and from the C down to the G is a fourth down. So 5 up, 4 down, and down means just inverted. Okay, so this is 3/4. If you go 4 down, that's 3/4. Okay, just do it, and you'll find 9/8. Okay, let's put in this number here in our little drawing. This is up here. Okay, this is this little bow up here. Let's remove the keyboard, and let's now put in, instead of string length, we now talk about frequency. So this is low frequency, high frequency here, and they are in this relation. And now let's compare this with what is called the epoch tone. This is exactly the same. So we have now understood how the Pythagoreans did that. And this, what is called here the epoch tone, is this full step from F to G, say. And it's called on top of 8, meaning that 9/8 is nothing else but 1 plus on top 1/8. Okay, and then all these other things here in the Greek expressions. So that has been now justified. But until now we have only, let's say, C, C prime, F, and G. So this is not much, right? But now comes this Pythagorean idea that in fact you don't need the fourth, the musical, because from F, low F, to C is a fifth, and from C to G is also a fifth. So you only need fifth. You only need 3/2. You only need fifth steps. And that's how they do it. So you start on this very low C here. You always go fifth up. So C, G, D, A, whatever, E, something, something. Then you switch to the black keys here. And then you arrive at this F here. And the next step would bring you to the C. And then you close the things. And you fold back all your notes, which are too high, so to speak, into the base octave, which ranges from this C to this C here, by just divide by 2. Okay, because that gives you an octave lower. Mm-hmm. Okay, and in this manner now you have constructed essentially the keyboard. You start here, and then we have this half-tone step do, 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 until here, and then it starts all over again because this is the next C here. And in musical notation, you would write something like this, what is written here. So these are the 12 keys now reconstructed from this tetractys. The 7 white keys, the first 7, and then the black keys, the 5. So that the idea is then a stack of 12 musical fifths equals equals 7 octaves. Well, not quite. But not quite comes in a moment. What you get here is the so-called 12-tone chromatic scale. We just constructed it. And you also get what is called the circle of fifth, and many of you have had to learn this in school maybe. Okay, this is the circle here, C, G, D, A, and so on, going around and back. Well, the problem is that this fit, 12 musical fifths, makes 7 octaves, is not the case. This fit is not perfect. The circle has a, let's call it a glitch, okay? The last one brings you a little bit over the edge here. This is from a drawing from a book by my good friend Johannes Euler, who wrote this book on Johann Sebastian Bach's struggle and Werkmeister's struggle with tuning organs. They had a real problem with that, and they came up then finally with a solution, which is called, I think, Werkmeister 3 tuning or something. It's a very interesting book. I highly recommend that. So the fit is not perfect. And that is, of course, as we all know, okay, because we are educated mathematicians, you cannot make 3/2 to the power something equals 2 to the power something. That doesn't work because 3 is a prime number different from 2, so that cannot work. The correction factor here, this is this one, it sounds small or looks small. It's only a very small correction, so it shouldn't matter. Well, listen to this. So this little glitch you saw in a few seconds ago, if you play these 2 notes together, then it sounded like this little horrible thing with these how's it called? Schwebung in German is it called? I don't know. It doesn't sound nice. And if you have a choir where the one stays on this initial C and the other one after singing arrives at this a little bit higher thing, okay, if they sing together, it sounds horrible. This is also called then, the total thing is called Wolf's fifth, Wolfsquinte. And of course, since 3 and 2 are coprime, this has no solution in integers. Yeah, it's absolutely clear. Leonardo Euler kind of figured out that you can find approximate solutions to this problem. The problem is written up here. And one solution would be very bad, that you have 2 fifths, and that should make 1 octave. Well, it doesn't, because if you have 2 fifths, you go from C to G to D. This is a 1 tone step away from the intended C. You can also make 5/3, meaning that you take a staple of 5 fifths, and then well, you hit almost 3 octaves, but you are half tone away from that. And the one here which we are using is 12-tone chromatics. There were other propositions made, in particular Arnold Schoenberg's proposition here with 53 in an octave, but you can't play an instrument like that. Okay, but if you think that is all bogus, no, it's not. In the early Renaissance, they tried to really play around with these possibilities, and this is a drawing from Nicola Vincenzo's book on ancient music adapted to modern practice. Okay, so he constructed this kind of device to go around this Pita. Okay, let's summarize this. The idea here of this Pythagorean tuning is essentially number driven. Okay, the anecdote with this MIDI or so, it only serves to illustrate that the idea that everything must come out of this tetractys is correct. Okay, so it's a kind of really dogmatic approach to the world. We find a fifth nice because tetractys says so. Okay, that has changed, and there were these difficulties. These difficulties with the Pythagorean tuning pop up in particular if you go to polyphony. So if you have several voices. Until the late medieval ages, you only had these church, let's say, singing, which has only one voice, then you don't care too much. But if you have several voices, then you start to care about this Pythagorean problem. And then this whole thing was modified during the Renaissance. In the Renaissance, the irrationals were essentially introduced. During Pythagoras times, that was not allowed. And even if you read Kepler's book, there is sometimes he mentions so-called unspeakable numbers. And these are the irrationals, like square root of 2 or something like this. Funny finding, this is Michael Stiefel. He's a German mathematician, and like everybody, a monk and a reformer and something like this, and like anybody else during their times, he wrote a book on mathematics, called here the Arithmeti, sa integra. Okay, fine. And in a certain chapter, he talks about the division of the Pythagorean full tone. The full tone Pythagorean, you remember, is this 9/8 in frequency or 8/9 in string length relations. And he wanted to take the so-called geometric mean, as we just did for the octave, okay, which gave us this devil's tone. And for that, he has to introduce the square root. He has to take the square root of, in this case, 72. Okay, but there was no sign for square root. Yeah, so he just invented it. And you see it here. This is this, I don't know why my printer didn't do this one here, this line. So this was the sign he invented just to talk about the geometric division of the Pythagorean full tone. And the funny thing is that ever since, we have this sign in our alphabet of mathematics, okay? So he was the inventor of that. Talking about some musical problem. Even more funny, this person here, Giuseppe Zarlino, again, a music theorist and composer and whatever, and he invented many things. And among others, he was the first one to propose this, what is called the equal temperament, and which has to deal with this 12th root of 2 for each halftone step. And now he could compute this, okay, without any pocket calculator, computer or something. Actually, he did not compute it, but he constructed. He gave a prescription for the exact construction of the 12th root of 2, and here's this.
A question, Martin?
Yes. Yeah, go ahead.
Was he using this notation already with 12 roots?
No, he was not, but he was talking about equal steps.
I see.
Okay,
okay.
And if you go get to Stiefel, certainly Zarlino knew of this sign, okay, but in his text, it doesn't appear. He just wants to have so-called equal step. And that amounts to the 12th root of 2, and he constructs it, this 12th root of 2. Here we go. This is the construction. Until now, I have understood 80% of what he is doing here. He is essentially applying Euclid geometry and a little bit of Pythagoras in order to construct these, what is called frets. These lines here, these are the frets. This is a fretted instrument, a lute. And he was, for example, this one here, the prima divisione, that is the, what we just had, this devil's tone, okay? This is exactly now relates to the square root of 2. So, and then the others here, well, anyway, okay. So he does that without any calculator, without any computer, not even doing arithmetics, he just does geometry. It's a kind of analog computer for things. Let me just wrap up this chapter on Renaissance here. The father of Galileo Galilei, again, a lutenist, composer, and music theorist, of course. I mean, everybody was at that times. He was the first one to find out that the frequency is actually of a swinging string is actually proportional to the square root of the tension. Okay, I will come to that in a second. And he also found some approximation for this 12th root of 2 here, which is 18/17. So the finding that the frequency is actually proportional not to the tension, as this artist here thought if he hangs these weights here, 16, 12, 9, 8, tralala, at these strings, but it's proportional to the square root. So if this instrument now would be played, it would sound like this. Okay, horrible. So the artist didn't know that it goes with the square root and not with the weight itself. Now this is Magnum Mercer. Again, what do we have here? A monk, well educated, also in mathematics. You know, he was essentially the father of the Mercian prime numbers, and this is just a little bit here. In 2018, there was a computer cluster who identified the largest known prime number. This is well, having these kind of how many? 23,200,000 whatever, something digits. Okay, it's a Mercian prime number which has this form here. But he also wrote, except for that, for the prime number investigations, he also wrote a book called Harmonices Universelle, as everybody did at these times. Here we go. And he, in fact, now found the right formula, or he essentially derived the right formula for the frequency of a swinging string. This W here is the weight you put here. Mu is some characteristics, some material characteristics. And the L is, of course, the length of this whole thing. Okay, so, and he was the creator of what is called the Overtone series, which you just saw. This he figured that out, that if you have a string, it can have these various overtones. Okay, so, oh, sorry. Let me go back. Oh, it's already very late. Could you give me 10 minutes or so?
Sure. Go ahead.
Okay. This now concludes the Renaissance. Okay, the Renaissance was really very ingenious in inventing new things and finding out lots of things, and which always relates physical things like playing around with these strings, mathematics, the division of string, and music, what is consonant and what is dissonant. Now let me, for the last part of this talk, I switch a little bit and I go a little bit into a very interesting subject, which is this book I was referring to in the beginning, which my colleague translated from Latin into German. This is called Random Music. There is a whole bunch of people out there in the internet. They are playing around with what could you do with random music. And this is in fact random music.
Again, we do not hear you.
Okay, so this, what you heard was random music. There is a whole bunch of people out there in the internet who have fun in composing various random musical pieces. This is one where we just translated pi, the great invention of Leonardo Euler, into a random sequence, of course random because you know it's a transcendent number, into a random sequence of tones. Okay, so I don't have to. Euler was really a genius. I think he's the only scientist who, after he died, published 220 papers or something like this. There is still an ongoing project to essentially make an edition of all the papers of and writings of Leonardo Euler. It's not finished yet. Okay, I don't have to introduce him as a person to you because you know Leonardo Euler from many contexts, but maybe you don't know that he wrote several, not many, but several pieces on, again, music, of course, what else? And this one is very interesting. It's Tentamen Novae Theorie Musicae. So he makes an attempt for a new theory of music. And here he gives you a number theoretic function to calculate the sweetness or the amenability of a musical piece. So whether it's fantastic, semi-fantastic, bad, or ugly. Okay, and this formula appears here. Let me remind you of this harmonic series, and let's concentrate on this, what is called the major triad, C-dur accord, with these frequency relations here, which you have. And there is a prime number in the game. with Pythagoras, you only had the prime number 3 in the game. Okay, now let's concentrate that you also allow for the prime number 5. And now Euler realized that if you have that, which is called 5 limit tunings, all the frequency relations, etc., pp., they can be always written in this form. So there's some power of 2, there's some power of the musical 5th, Q, this is the musical, and there's some power of this, which is the musical 3rd in just intonation. And so, in other words, everything can now be mapped onto a, well, onto this set here on the Z3, and meaning that somehow you now have a crystal lattice, because it's 3-dimensional, you have these 3 possible numbers. But because of octave identity, meaning that somehow if there's a tone and then there's the same tone an octave higher, they are considered to be in the same pitch class. So you can even get rid of these powers of 2. You don't need them, okay? Because they just give you octave jumps. So you are back then on a lattice, which is characterized by these 2 numbers here. And you can make this lattice now. Here this is it's now a triangular lattice for some reasons, and which is better to play with. So this is your root tone you start with, then you go a 5th up, and then you go what is called here a minor step down from G to E. This is this minor step, and then you go from okay, you can close the circle, so to speak. Okay, this is the major triad here you just saw in this what is called the just intonation. And this other triangle here, this is nothing else but the minor triad, okay, fine, which is this, yeah, minor, A, C, E. The point, however, is, and that I hope you can see that here, if you take as your starting, did I do that? Yes. If you take as your starting point C and you go to this B here, you want to reach this B, you can do this in 2 manners. You can either go from C to B, or you can go kind of this way here. Yeah, there's another one. These are not the same pitches, okay? Because we are now playing with these, yeah, well, minor and major steps and 5 steps. Okay, so the first one goes C, F, and then you reach B. I cannot see my own screen here. This is horrible. You know, I can. I hope, yes, I can. So you go from C, upper line here, C, G, B, and that's a 5th step, and then comes this small, diminished 3rd step, 6/5. That gives you 9/5. So this tone to this tone has a frequency relation 9/5. If you go differently, this would be this path here. And the lower thing would be this path, from this C to this one here. You go first a 4th, which is 4/3, and then another one, 4/3, 16/9 relation. And these 2 tones now, they are related by this fraction, and this is 81/80, meaning that these 2 notes sound different. They have a different pitch. And if you have a choir who essentially goes this path, and the other part of the choir goes this path, then they will end up in slightly different notes. Now, the question is then, can you find a way to kind of avoid these problems? And we will come to that in a minute. And Euler's answer is yes, you can. You can avoid that. Okay, let me conclude this here. Right, okay, we did this already here. Okay, so this thing here, upper line is, let's say, the chord unfolded here in Pythagorean scaling or in tuning, and this one down here is the one in just intonation. Okay, I don't need that. Now, Euler's way out is, okay, there is a measure which measures the sweetness of a chord or a melody or whatever, and it's called the Gradus Suavitatis, the grade of sweetness. And formally it's a map from the naturals to the naturals, and you take some number, and this, what is written here on the right side, is essentially the decomposition of this number A into its primes and the exponents of the primes, which is here. You can read off the meaning of this P and E you can read off here down here. A is a natural number. What is it? It's the least common multiple of your chord tones, called chi1 to chi-n. Okay, and that how does that come? Why do you need this least common multiple? And Euler explains this to us. Here is the explanation. So take a musical fifth, and just you don't know yet that these are sine waves, the pure tones, but he pictured them as this kind of pulse trains. So this is the pulse train of the higher note, the G, and this is the pulse train of the lower note. Yeah, and you see, if you have these two here in between, this is the duration, and here we have then 3. Okay, it must be so because it's a musical fifth. Then the least common multiple is 6. Okay, so the smaller the least common multiple, the more often it happens that these two things are in consonance. And the larger this least common multiple is, it means that the fewer, the lesser they are in consonance. And his idea is that the more often they are in consonance, the nicer it is. Okay, that was his idea. So the smaller a, the better. A is the least common multiple. But that is not enough. He also knew that there are somehow these numbers, they can be complicated or simple. For example, 7 is a simple number because you cannot make any further prime decomposition. It's a prime. And then there's a number like 6, for example, which is smaller, so it should be nicer, but it's more complicated because it consists of the product of 2 primes. So he said, well, then I have to take this least common multiple, this a, which is called the exponent, and I have to essentially make this prime number decomposition. And then he comes up with what he did here. And then he did, okay, and then the Gradus Suavitatis, this is this formula gamma of this chord, equals this whatever here. And now we can make some examples. The unison is just the tone with itself. It's kind of, it's the sweetest of all. Careful, the smaller this gamma, the sweeter the chord. It's a little bit counterintuitive, but so it is. So the tone with itself has sweetness, has the highest possible sweetness degree, which is 1. Then the octave is very sweet, it has 2. The double octave is okay, it has 3. And now let's go for the fifth. It has sweetness 4 because if you go, okay, C over G, this is this relation here, the least common multiple, as I told you, is 6. So it's 2 to the power 1 times 3 to the power 1. Insert these things over here in this formula, and you find that it's 4. So this is the fifth step. It is 4. And now let's check the triads, the Dreiklänge. The major triad in this just intonation, which includes the prime number 5, has sweetness 9, which is kind of really still nice. But if you take it into Pythagorean tuning, which is with this 81 over something there, this very horrible large nominator and denominator thing, then it becomes 15, which is horrible according to Leonardo Euler. Okay, so you should not use Pythagorean intonation of your chords, but in this case of this major triad, you should use what is called the just intonation. Fine. Now you can go, you can look for all these gamma values from 1 through, I did it to 14, what happens there, what kind of intervals or so play a role. I don't go through these details because it won't interest you too much. I will just, some last 3 minutes, what comes out of this, okay, of this investigation of musical sweetness with a number theoretic approximation approach. Well, there are some mathematical features of this gamma. It is subadditive, and it's a metric it constitutes a metric on the Euler lattice. And that has very interesting application called scale rationalization, which is a problem which is most likely, or I think it's NP complete. It's a paper by Alexander Graf, where he says, okay, what is the problem of scale rationalization? The following problem: you record, okay, you go to your studio, you record a piece of music, and then you want to publish it as an MP whatever file. Now, it may be so that this file is very, very fat because, because you're using very interesting modulations in your melodies and so. And now the idea is, instead of taking the analog signal and digitizing it in a kind of simple-minded fashion, do the following. First take your signal, analog, digitize it, and then try to find for each, let's say, time bin, try to find a substitute in terms of adapted fractions for your musical intervals. And you prescribe, for example, the maximum size of the denominator and the maximum size of the numerator, and then you rationalize your scale, okay? And then doing so, your file size will shrink by a factor of 100 or 1,000. So it's a very useful application, and you can use, if you want to, you can use this this Euler metric there to do that. And in fact, it has been done by somebody else who made a slight modification to this sweetness function here, Clarence Barlow, who is an electronic musician. He did that. Okay, so that concludes my talk, by the way. And thank you, Leonardo Euler, for this great insight. He's something like the Beethoven of math, right? I think there is a very interesting quote by Frobenius. Euler lacked only one thing to make him a perfect genius. He failed to be incomprehensible. Right. So, and then there's a poem which I love, okay? E to the I pi plus 1 equals 0. Made the mathematician a hero. From the real to complex, with our brains in great flex, he led us with zest, but no fearo. Yeah, so that concludes now in Latin, yeah, a quote from Isidore of Sevilla. Music is a discipline that speaks of numbers which are found in sounds, but because this is a physics talk, I have to stop with the physicist, and this is, of course, who else? Richard Feynman. I will read it to you. The idea that the natural frequencies, which we are talking about recently, are harmonically related is not generally true. It is not true for a system with more than one dimension, nor is it true for one-dimensional systems which are more complicated, nonlinear, than a string with uniform density and tension. So full stop to this project. Thank you very much for your attention. And now, of course, the paper is open. I mean, from my point of view, the paper is open for discussion and questions. But you may want to go home and eat something because you are tired, because I spoke too long, actually 1.5 hours. Oh, wow. No.
Okay, Martin, thank you very much. Let's applaud the speaker. And I think we have time for some questions, one or two. Go ahead if you want to ask.
So, I raise my hand, so maybe I will.
Sure, go ahead.
Try to ask something here.
Hi, Marek.
Hi. Namely, I think this is also a kind of, which I like very much, a vindication of medieval times against Renaissance. So, but the idea that the celestial motion is more complicated, so it's not commensurate, is quite early, because this is already from 14th century. I think the name in English should be Nicolo Oresme, who considered and maintained that the motion of spheres is incommensurable, which is more than, for example, something which is done for the well-tempered scale, because in fact, in this scale, you can calculate all sounds from one sound by multiplying this or taking the power of square root of 12. I don't know what was his opinions about music. Maybe he didn't write anything about music. But this idea, from this point of view, the idea of Kepler, or I would say the notorious Titius Bode law or something like that, who wanted to put some proportion, some natural number proportion into celestial motion, was a step backward, or was a step back from this medieval idea.
Yeah,
So,
right.
so my question is actually, when you talk about the random music, it was not concerning the randomizing frequency, but rather randomizing the intervals.
Yeah,
Yes.
that's right. Yes. Okay. This random music thing, you are completely correct. You can play around. You have to play around not with the absolute frequency, but with the intervals. Okay. First, absolutely correct. Second, you can, and this, of course, this community of randomized music producers out there, they also use, you can change the instrument, you can change, what else degrees of freedom you have, you can take in. The length of a tone, what else can there be? I don't know. I mean, many things, okay? This was a very simple one. I just took my piano and I made this this primitive thing. But you are right. The Kepler, in fact, this was 1817 or so. He was, to some extent, he was really a Pythagorean.
Yes, exactly. So, for example,
200 years before. Now, how many years? Let me think.
Niccolo Foresta was from 14th century. Okay, so it was maybe 200 years before when he put this idea that it could be incommensurate.
Yeah, that is right. So, but why was he Pythagorean? Okay, because he was also, as you know, he was a Protestant, and he was a strong believer. So his research, let's say, his project was to unravel the harmonic principles, which the Almighty has imposed on the world. First, okay. Second, we as humans, as children of God, have been equipped with the ability to recognize these harmonic principles. So his research project was he wanted to find out these harmonic principles. And of course, that is exactly something very similar to this Pythagorean idea that there is a one thing, in the Pythagoreans it's this tetractys, whatever, it's kind of holy, and everything comes from that.
So that's why I said that the idea of Foresta was completely different, because you cannot calculate the other frequencies of motion from one. And here, right, even with well-tempered scale, you can do this. Okay.
No, you cannot. Okay, absolute frequency you can never get. And also
absolute no, but intervals. I mean, okay. So
yeah, the intervals. Yes, right. But why not? I mean, the Kepler approach was just take the angular frequencies. For the melody of a planet. His greater problem was to essentially pitch the how's it called? To pitch the relation of the planets, okay? Because you know Saturn is very slow.
Yes.
And Mercurius is very fast. So, and if you would take a one-to-one translation of these velocities, he would go from infrasound to how's it called, this ultrasound or something. So he had to do something with that. He also found a way which convinced him to do something. So you could hear then this piece I just displayed to you.
Okay, Martin, could I ask you?
Yeah.
Do you know whether Chinese music or Indian music was also based on similar arithmetics and considerations of that same kind?
No, the Chinese is more or less what is called pentatonic. More or less, meaning that there are some deviations. So what is pentatonic? Pentatonic is if you look at the piano and just take only the black keys, okay, that's a pentatonic scale. That is, and you can even make this experiment. You go to whatever instrument you have, and you do that, and you can play randomly around, and you had, oh wow, I am in China, kind of.
Yes, that's true. If you play only the black keys, it is a Chinese music. But these pentatonic scales appear also in European culture, especially in folk music. Okay.
Yes, that's right. Yeah. Now and then the Arab scales are very interesting because they you know that, okay? If you listen to Turkish music or to some Arab music, they have this quarter tone steps in their scales, and they certainly did not construct this in this kind of dogmatic Pythagorean way there. They did it more or less what sounds nice will be played. So that gave them this their scales. And in fact, I should show you that, because that is highly interesting now. I have to go here, and I have to go here, and I have to go here. Just give me 30 seconds. No. Why isn't it in here? Anyway.
So these microtones were quite recently, I would say, discovered in the Western music, or introduced. Okay, this microtone music.
Yeah. In Western music, it was Schoenberg and others.
Yes,
right.
yes.
But in Arab music, it was introduced.
Exactly. So this
I wanted to this. I have to find this. There is, okay. I will tell you what it is. In 1950. Jerzy Kijowski, yeah, you okay, in a minute. In 1950, the archaeologists dig up a clay plate which has this conifers, this Babylonian writings on it. It was then dated 1500 before Christ, and when trying to decipher this, they realized that there's, on the one hand, there is a, let's say, a text, namely some prayer to the goddess of the moon or so, and below that there is a string of numerals, and it was for a long time it was completely unclear what is that, and then they found, well, that is nothing else but a melody written in this numerical fashion, and it was then by the so-called discipline of musical archaeology or something like this, they could translate this into a melody, and then they could play it. And I want to find this piece. And okay, even if I don't find, the point is that until 1950s, the Western civilizations were absolutely convinced that this Pythagorean model of music, this 12-tone thing and everything, that was an invention by the old Greek, like everything else. No, it was already there 1,000 years before that, because they used the same kind of scale with this fifth and this fourth and this thirds and the sixth and the full step and the half step and all these things, okay, were already present 1,000 years before Pythagoras. So that was a great shock. And there was even a New York Times article which appeared, I think, in the 19-something 70s or so, that we have to put at rest this idea that music comes from Pythagoras. That is absolutely not correct. Okay, so there was a question by Jerzy Kijowski.
And that's the last question. Jurek?
Oh, excuse me, something. Do you hear me now?
Yes.
Okay. So rather a comment than a question, because all the entire talk was about proportions, and that's true, because for me also music is proportions. However, there are among us very exceptional people who have the so-called absolute ear, and they are able to hear the absolute frequency. They are really terrible. Some of them, I had a friend of mine who was a very good musician, but he always complained during the concert that, oh no, the orchestra has put the pitch a little bit too high.
Very nice, very nice.
I'm unable to hear the absolute pitch, but there are some such people among us.
Yes, absolutely, very nice. Okay, that is true. There is a whole community out there which are complaining that the concerto pitch, which the international standard is 440 hertz on this middle A. Okay,
it is never observed. Now it is just higher. By the way, 100 or 200 years ago,
yes, it was lower.
435.
Yes,
Therefore,
yeah, that's right.
Pianos are not able to follow the actual pitch.
Yes.
Because
that is right. Okay, but the industrial standard is this 440 hertz. So if you buy an electronic instrument, an electronic piano or something like this, it is exactly tuned to this 440 hertz. And
but the orchestras never follow it.
Yes, that is right, because they are absolutely
violin. They have always tendency to go a bit higher, a little bit higher.
Yeah. Okay. So, for example, Herbert von Karajan with his orchestra here, the Berlin Symphonicos, he put the pitch higher.
Yeah.
So he was at 446 or something like this, because then the violins sound more brilliant.
Yeah.
Okay. Then there are other groups who go lower,
Yeah.
and in particular, there is a old group who says, well, we cannot, 440 is a sin, we have to go to 434 because there is an ionospheric resonance which essentially tunes in with this 434 and everything else is a sin. Okay, now if you talk about absolute how's it called, absolutes Gehör, absolute hearing, then these are people who essentially have been, let's say, socialized or educated in a certain environment where certain songs are sung in a certain pitch, with a certain pitch. And from then on, it is so that they really can hear that if another person sings, okay, so they have been educated in a system where 434 is the concerto pitch for A. And then they go to a symphony or concerto where they are tuned to 442, say. They suffer like hell because they have this absolute thing, and they can distinguish, and they really suffer then. That's right.
Okay, I think that's about time to stop. Thank you, Martin, again. I hope to see you in person one day again.
Right.
And let's applaud him again until the next colloquium.